In Chapter 7, questions 18 and 17 and 18, they're asking you to convert moles of one thing to moles of another. And the trick is that you can use the coefficients in the balanced equation. And remember, those coefficients are the numbers in front of the compounds. You can use those coefficients to create conversion factors between moles of those two different things. So let's see how that's done. Now in A it says how many moles of O2, so this is what they are asking for. We're looking for moles of O2 are required to react with 2 moles of H2. So that's what they're giving us, 2 moles of H2. Okay, as with any conversion, in order to do the conversion, you need a conversion factor that relates the two units. So how do moles of H2 relate to moles of O2? So how do those two units relate? And we can figure that out by looking at the coefficients in the balanced equation. So the coefficient in front of H2 is 2. And so we can write 2 with the number of moles of hydrogen. For every 2 moles of hydrogen, we will need the coefficient in front of oxygen is 1. No number is written there, and so it's an implied 1. And so we will need 1 mole of oxygen. So for every 2 moles of hydrogen, we'll need 1 mole of oxygen. And that gives us a conversion factor to relate the two units. So anytime you do a conversion, take the number that you start with, always write a multiplication sign, a fraction bar, in the units that you start with, so here that's moles of H2, those units are going to go on the bottom of the fraction so that they'll cancel out. So the moles of H2, we'll go to the conversion factor and put the side of the conversion that has moles of H2 on the bottom. Going over the fraction bar is like going across the equal sign. So on top, we'll have the other side of the conversion factor, 1 mole of O2. So moles of H2 will cancel out because this first one is on the top and the second one is on the bottom. We'll be left with moles of O2, which is exactly what we want. And you just plug this into a calculator. So 2 times 1, 2, divided by 2 is 1. So we'd be left with 1 mole of O2. And that would be the moles of O2 that you'd need to react with 2 moles of H2. All right, let's do a similar procedure for B. It says how many moles of H2, so now we're looking for moles of H2, are needed to react with, here's our number, 5 moles of O2. So they're giving us 5 moles of O2. Oh, also another thing, you see that mole here is MOLES. The abbreviation for mole is MOL. So MOL is the abbreviation for MOLE. So you could write it either way. All right, so we have these two units. It's a conversion problem. In order to do the conversion, we need a conversion factor that relates those two units. So how do moles of oxygen relate to moles of hydrogen? And to answer that, we're going to look back at the balanced equation. That's this equation up here. Look in front of oxygen. The number and the coefficient to the left of oxygen, right in front of it, is 1. Now it doesn't look like there's anything there, but if there's nothing there, it's an implied 1. So there's an implied 1 right there. And then, what's the coefficient in front of hydrogen? Well, 2. So we'll write 2 with the moles of hydrogen. Oops. So now we know that for every 1 mole of O2, we'll have 2 moles of hydrogen. Now that we have the conversion factor, we can do the conversion, take the number they give you. Every time you do a conversion, write a multiplication sign and a fraction bar. The units that you start with are going to be the units that you want to go on the bottom of the fraction so that they'll cancel out. So here, that's moles of O2. So we'll take the part of the conversion that has moles of O2 and we'll put that on the bottom. Going over the fraction bar is like going across the equal sign. So on top, we will have 2 moles of H2. Moles of O2 will cancel out. We will be left with moles of H2, which is what we wanted, and we just have to do the math. So multiply by the top, 5 times 2, hit enter, so that's 10. Divide by the bottom, divided by 1, enter. You should get 10 moles of H2, and that would be the answer for this. So that would be the number of moles of H2 you'd need to react with 5 moles of O2. All right, let's try C. It says how many moles of H2O? So this is what they are asking, moles of H2O. How many moles of H2O form when, and here's our number, 2.5 moles of O2 react. So we have 2.5 moles of O2, and we want to convert that to moles of H2O. Now to do that conversion, we need a conversion factor that relates those two units. So how do moles of H2 relate to moles of H2O? And to answer that, we're going to go to the balanced equation. So in front of O2, you can see there is a 1. It's an invisible 1. No number is written there, so then 1 is implied. So we can write 1 with a number of moles of O2. In front of H2O, there is a 2. So we can write 2 in front of the moles of H2O. So that gives us our conversion factor. We can do the conversion, take the number they give you. Every time you do a conversion, write a multiplication sign and a fraction bar. The units that you start with on top are going to go on the bottom of the fraction so that they'll cancel out. So here, that's moles of O2. So we'll take the side of the conversion factor that has moles of O2 and put that on the bottom. Going over the fraction bar is like going across the equal sign, and the thing on the other side of the conversion factor will go on the top of the fraction. Moles of O2 will cancel out. We will be left with moles of H2O, which is exactly what we wanted. And then you just plug it into a calculator. So 2.5 times 2, enter, that's 5. Divided by 1, enter, so you would have 5 moles of H2O. So when 2.5 moles of O2 react, you would get 5 moles of H2O. Okay, question 18 is the same sort of thing, except here they're giving you a different equation, but you'll see the process is really the same. They say ammonia is produced by the chemical reaction of hydrogen and nitrogen, and this is actually a fascinating equation. The air that you're breathing right now is 79% nitrogen, mostly nitrogen. Hydrogen gas you can get pretty easily from a petroleum plant when they're refining stuff. And then you can react those two to make ammonia, which is a precursor for fertilizers. So you can basically make fertilizer out of thin air. That's what this reaction is. And that reaction goes to feed around 1/3 of the world's population right now. It's called the Haber process, if you want to look that up. It's very interesting. So the process for solving this is very much the same as before. They say how many moles of H2? So we're looking for moles of H2 are needed to react with, and here's our number, 1 mole of N2. So in order to do this conversion, we need a conversion factor that relates these two units. So we need to know how moles of N2 relate to moles of H2. And to do that, we're going to look at the coefficients in the balanced equation. In front of N2, the coefficient is 1. No number is written there, and so there's an implied 1. In front of H2 is 3. And so the number that we can put in front of the moles of H2 is 3. So we know that for every 1 mole of N2, we'll need 3 moles of H2. Okay, now that we have the conversion factor, we can take the units they give us. Every time you do a conversion, write a multiplication sign, a fraction bar, and the units that you start with on top, here moles of N2, are going to be the same units that you want on the bottom because you want them to cancel out. So we're going to take the part of the conversion factor that has moles of N2 and put that on the bottom. Going over the fraction bar is like going across the equal sign. So on top, we will have the other side of the conversion factor, 3 moles of H2. Moles of N2 will cancel out, and we will be left with moles of H2, which is exactly what we wanted. You can plug this into a calculator. 1 times 3, and after the calculator does a whole bunch of quantum mechanical calculations, it gets 3 for that. Divide that by 1, and you get 3. So you'll have 3 moles of H2. So that's how many moles of H2 you'd need in order to react with 1 mole of nitrogen gas. All right, now let's try B. It says how many moles of N2, so that's what we're looking for, moles of N2 reacted if, and here's our number, 0.60 moles of NH3 is produced. So we have 0.6 moles of NH3. NH3 is ammonia. Okay, so it's a conversion problem. In order to do the conversion, we just need a conversion factor that relates these two units. So how do moles of ammonia, NH3, relate to moles of N2? And in order to get those numbers, we will go to the balanced equation. So in the balanced equation, in front of NH3, you see the number 2. So we can write 2 with moles of NH3. In the balanced equation, in front of the N2, you see that there's an implied 1. No number is written there, which means there's an implied 1. So we can write a 1 with moles of N2. So that's our conversion factor. We can take the units they give us, or take the number they give us, and every time you do a conversion, write a multiplication sign, a fraction bar, and the units that you start with are going to be the units that go on the bottom of the fraction so that they'll cancel out. So here that's moles of NH3. So we'll take the side of the conversion factor that has moles of NH3, put that on the bottom of the fraction. Going over the fraction is like going across the equal sign, so on top we'll have 1 mole of N2. Moles of NH3 cancel out. We will be left with moles of N2, which is exactly what we wanted. And then you just punch this into a calculator. 0.6 times 1, enter, divided by 2, enter. You should get 0.3. And so that would be the moles of N2 that reacted if you produced 0.6 moles of NH3. Okay, last but not least, how many moles of NH3? So that is what they are asking for. How many moles of NH3 are produced when, and here's our number, 1.4 moles of H2 react. So this is a conversion problem, and in order to do any conversion, you have to get a conversion factor that relates the two units. So we need to know how moles of H2 relate to moles of NH3. And to find that out, we're going to go to the balanced equation, and notice that in this balanced equation, in front of H2, we have 3. So we know that for every 3 moles of H2, go back to the balanced equation, look in front of NH3, 2 moles of NH3 are produced. So you'd write a 2 in front of moles of NH3. So we have our conversion factor. You can just take that number they give you. Every time you do a conversion, write a multiplication sign, a fraction bar. The units that you start with are always going to go on the bottom of the fraction because you want them to cancel out. So here, that's moles of H2. So we'll take the side of the conversion factor that has moles of H2, put that on the bottom. Going over the fraction bar is like going across the equal sign, so on top we'll have 2 moles of NH3. Moles of H2 cancel, and we are left with moles of NH3, which is exactly what we wanted. And so all you'd have to do is punch this into a calculator. So 1.4 4 times 2, enter, should give you 2.8, divided by 3, enter, and it should give you 0.933. So that would be the moles of NH3, or ammonia, that you would produce if you had 1.4 moles of H2 gas. So in questions 17 and 18, you would see how you can use the coefficients in the balanced equation. Those are the numbers in front. You can use those numbers to create conversion factors that allow you to convert from moles of one thing to moles of another.